We continue on the next section. Previously, the equation for heat convection is given by the Q equals to Q dot equals to H A times the delta T. So that equation will be the same. However, for different cases of heat convection, it will involve so many variables. For example, just now, maybe the Reynolds number, the flow itself, the friction, and so on. And because of that, therefore, because of this so many parameter involved, and then they come out with the dimensionless number. So for this session or this particular practice, I will only focus on the force convection. So basically this one. And basically we have two, free and force convection, and for each one there are their own dimensionless number involved. So the most common one will be Nusselt and Prandtl. Okay, so both have in both free and force convection. And then also we have Reynolds number, Grashof and Rayleigh. So for this particular practice, I will only focus on the force convection. So therefore, I will only touch on these three particular dimensionless number. So if let's say you go through any other references, for example, myself, I use Yunus Chenyal references. So there are different equation for different geometrical shape. So as for that, I will only introduce the general one, which is this one, and U. Nusselt number is given by the coefficient C, Reynolds number power of M, and then the Prandtl number power of N. So I will use this one, and then this C coefficient will be very much depends on the geometrical shape. So based on these two, free and force convection, for each one we can divide it into three major section or types of geometrical shape. Basically vertical, for example, for free, vertical plate and cylinder, horizontal plate and cylinder, and then spheres. So for each one, it will have its own Nusselt number equation. And same goes for the force convection. We have flat plate, either laminar or turbulent. We have cylinders and then spheres. And however, for this subject, I will only use the general one just now. And U equals to C RE power of M and Prandtl ER power of N. So force convection. So Nusselt number is given by the very general equation, which is the H, the coefficient of convection, times the characteristic length, and then the K, conduction coefficient. And also this one is given by the C, coefficient based on the types or geometry, and then the Reynolds number power of M, and then the Prandtl number power of N. So to make our life easier, so this table basically already categorized types of geometry as well as fluid, and then for different Reynolds number, this already generate the equation for the Nusselt number. So for example, for square, and then the range of Reynolds number between 5,000 to 100,000. So the Nusselt number is given by the C, which is 0.102. Reynolds number power of M, so M in this case is 0.675. And then the Prandtl number is power by 1/3. Okay, so for any cases, first we need to check the types of geometry. So this So all these are the very basic or standard geometry lah. Because in real practice, sometimes the geometry might be a combination of, for example, maybe a circle with vertical plate. And then, of course, the Nusselt number and then the Reynolds number will be changed lah. Okay, so Nusselt number is given related to this kind of situation. For example, this is internal flow. So we have a pipe wall, and then sorry, it's not really a pipe. So let's say we have two plate. So T2 and T1, and T2 is higher than T1 in terms of temperature. So by right, the temperature we transfer from T2 to T1. And then the characteristic line in this case is the distance between T2 and T1. And then here is given the characteristic line, so the D in this case. Next one is the prime number. Prime number is the relative thickness of the velocity and the thermal boundary layers described by the prime number, which is the molecular diffusivity of momentum over the molecular diffusivity of heat. So it is mean that prime number is the ratio of momentum, which is the speed of the molecule. Okay, the movement of the movement of the molecule due to the speed itself over the movement of molecule due to the heat. So that ratio will determine the prime number. Then we can see here for different type of fluid, for example from metal to glycerin. So metal with lowest prime number, and then the glycerin with the very high prime number, 2000 to 100,000. Prime number for gases is about 1, which is indicate that both momentum and heat dissipate through the fluid is about the same. Again, momentum and heat dissipate through the fluid is about the same. And then heat diffuses very quickly in liquid metals. So for prime number very much lower than 1, for example the liquid metals. So heat diffuses very quickly for lower prime number. So this one makes sense lah. And then for very high prime number, for example oil and glycerin, it is very much slow relatively. So that's about the prime number. Okay, next one, the Reynolds number. So Reynolds number should be very common one based on fluid mechanics. So Reynolds number is given by the rho ux over mu just now. So x in this case is the characteristic length. Okay, so I will straightforward show you how to solve the force conversion equation. Okay, now let's say for a flat plate, engine oil at 60 degrees Celsius. So we have an oil here, okay, moving at constant speed, 60 degrees Celsius, and then the speed at 2 meters per second. Then we have a flat plate whose temperature is 20 degrees C, so the T at the surface is 20 degrees C. Determine the rate of heat transfer per unit width of the entire plate. Use Nusselt number of C 0.664, Reynolds number power of 1.2, and then prime number power of 1.3. So for the given question, so the very first thing is normally we need to find the TF, is the average between the surrounding and then the surface temperature. So in this case 20 plus 60 become 80 divided by 2, then we have 40. So from this 40 we will check the properties of this engine oil. So for example in this case we can refer table at 40 degrees C. So the density is given is 876 kilogram meter cube. And then the part number is 2870. The kinematic viscosity is 242 times 10 power of negative 6 meter squared per second. And then the conduction coefficient 0.144 watt per meter squared Celsius. So the very first thing we need to determine the Reynolds number. Okay, so based on this one, first we need to determine the Reynolds number. So from the Reynolds number, then we can use the Nusselt number, or from the Reynolds number, then we determine which Nusselt number relevant to that particular case. But for this case, it's already given the Nusselt number. So just determine the Reynolds number and then use this formula in order to determine the Nusselt number. So from the Nusselt number, then we're going to determine the H value, which is the convection coefficient. And then from there, we can determine the Q. So based on this example, you can see that so Nusselt number will the H is very much depending on the Nusselt number. So different Nusselt number will give different H value. So therefore, based on the same equation, Q equals to HA delta T. So the changes for different cases of force or free convection is basically on the H value, which is based on the Nusselt number in this case. So let's go. Yes.